Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome to my talk. Actually, I want to spend a few words on our group before I head over to the talk, actually. So we are a system software group at FAU, which is not the Florida Atlantic University, but the Friedrich Alexander University, but that's still a long name, not able to fit on any badge. So we do two things in our group. We do operating system research and distributed system research. And in addition to that, we have a couple of people, like 4 PhD candidates, working also on energy efficient system software. And I will today talk on our latest research. I will first have a introduction into energy aware systems in general, and then I will give a presentation I will be giving on Sunday at Trials. I think Andrew has also a paper on at Trials. Yeah. You don't have a backup for that talk? Okay, all right. Okay, so to motivate my talk, I want to talk about two mobile computing systems. Actually, the first mobile computing system on the planet. It's Osborne 1. It was released back in 1980. And I was wondering, okay, what has changed in those 30 years since we got the first computing system? Yes. Oh, what? What's a bold claim? Oh, it was the first mobile computing system, at least. At least it was advertised as such. Actually, it was advertised to be the first computer which fits beneath the front seat in a plane. So that's what it made it mobile. It wasn't so practical to use. We'll see that in a second. But what did you think about what would have been the first mobile system?
Planes were bigger. Flying. Well, I'm pretty sure the moon landing.
Okay, right, yeah. Probably it's the first one which was generally available to the public. So. Okay, so if we look at the technological progress over the last 30 years, we can see that we did pretty well with regards to a few technical things like network speed, which has increased by a factor of 3.3 million, or storage, which has been increased by a factor of 1.4 million. Memory could be increased by a factor of 500,000. And what you probably have not yet recognized, there's a fourth box down here. Maybe someone wants to take a guess. What's that? Okay, good. Yeah, it's battery life in general. So actually, we were only able to extend the battery life from 1 hour for the Osborne 1 to roughly 10 hours for the mobile computers we are using today. And that's just the motivation for computing systems in general who have to deal with the resource energy today. So I will not only focus on mobile computers like that, but in general, from the smallest devices, smart dust, to the data center, we currently have an issue with energy.
Although
yes,
you've got raw capacity in the other 3 boxes, well, you've got utility in the lower one. I mean, if you put the utility in storage,
yeah,
the box might be much smaller because the software is loaded to install data storage.
Yeah, that's right, yeah. So, as mentioned in my introduction, I will first talk a little bit about energy proportional systems to get an idea what they actually are and how we can today optimize them from a software point of view, not from a hardware point of view. And then I would go and give the presentation of our trials paper, which is called Proactive Energy Aware Programming with Peak. If you have any question in between, just raise your hand and ask. So, if we go back to this Osborne 1 computer, you probably would have something like that if you look at the utilization compared to the energy consumption of the system. It's pretty much static. You didn't have any software knobs you could use in order to use energy saving features at hardware level, because there haven't been any at that time. And if we look at today's systems, it's probably something like that. If we are in an idle mode, we also use pretty low energy, but that increases with the amount of utilization we put on the system. And I was wondering, okay, how will this proceed in the future? So how will this probably change over the next years? And I took a look at this chip. It's an Intel Claremont prototype platform, which they have presented recently. That's a very good example for an energy proportional CPU. It actually scales from 3 megahertz to almost 1 gigahertz. So that's pretty good for at least the Intel machine. ARM chips come close to something like that, but that one is really something interesting for me because they actually made a publication with some numbers on it, which are interesting for me to look at. So this also translates into a nice proportional power consumption. So if we are running at 3 megahertz, it's down to 2 milliwatt for the power consumption of the CPU, and it's only going up to almost a watt for the maximum speed of the processor. On this following slide, which is out of that Intel paper, they show how the frequency of the CPU is compared to the total power consumption of the CPU. And the very interesting spot for me is the following one. We can see that if we use 25% of the maximum power consumption of the CPU, we're already getting 50% of the performance. So that's pretty interesting for us, especially if we put those numbers into a similar graph to the ones I've shown previously. It gives us an idea that if we only have an idle or a normal utilization, it will also make sure that the system is in a low energy mode. So this is very interesting for us from a software perspective because we can try to keep those busy moments at a minimum and try to shift our software to a normal utilization state in order to keep the system running at a low energy footprint at the longest time possible. Yes, please.
It seems that your instructions per cycle increases linearly with CPU frequency, right? Is that true for that chip?
Sorry again?
So you've
Yeah.
got a nonlinear power curve.
Yeah.
And then as you increase your frequency, you're saying I've got
Yeah.
50% of the frequency,
Yeah.
25% of the power. But
Yeah.
I have 50% of the frequency. Does that mean I have half of the instructions per cycle that I'll be executing compared to the max frequency of the chip? Is the throughput of the chip half, or is it just that the frequency is half?
I don't have numbers on that, so they didn't make a publication with the actual performance you get out of this frequency.
Right,
but
if it was a fourth,
yeah,
then
that's right. Yeah, that's true. Yeah.
I don't know. Although if I were going to guess, I'd guess it'd be higher because
Yeah, but
frequency
yeah,
is
yeah.
affected by the
Yeah.
memory delays, and well, you've got longer to wait for the memory.
slower your clock. That's true
Yeah.
too. Well,
Yeah.
then I don't know.
Yeah, we don't know. But yeah.
It's and also it's only a prototype. I'm really not sure whether this what they have presented. Yeah.
It just popped up as a
Yeah.
question.
Yeah, it's just, for me, something to reason about how it could be in the future and what we can do in case it goes like that. But, of course, you're right. If it goes a different way, we definitely have probably other measures to take to increase the energy efficiency. So if we look at today's developers, what they are doing to optimize their program code with regards to energy efficiency, they have a backward-looking approach. So normally you go into development phase where you actually write software, and after you are done, you probably test that software or you are deploying it to a customer. And this is usually the moment when you actually find a defect. That's pretty similar to a functional defect in an application, but it's especially true for energy bugs because it's usually a thing of non-availability of tooling infrastructure, so that people are not able to actually address energy efficiency at the time of development. And we are trying to address that at this time. So with our tooling infrastructure I'm going to present now, we are actually trying to keep the development time, the time where we are also optimizing for energy. So we try to really integrate the aspects of energy efficiency into the regular programming style or integrated development environment of a developer. Before I give the talk on peak on productive energy programming, I've added this slide just to sum up what else we are doing in our group with regards to research on energy-aware systems. So first of all, we had a publication back in 2011 at Hot Power at the workshop on power-aware computing systems, computing and systems, where we presented a system called SEEP, which actually analyzes program code for energy efficiency by first executing it with symbolic execution, extracting runtime complexity out of that, and then using energy models we obtained with the measurement device we have built in order to judge whether a change of the program code is going to change anything with regards to the energy consumption. And as a result of that workshop paper, together with the further development of the energy measurement device, which we actually presented as a prototype at that time, we now came up with our work on proactive energy-aware programming with Peak. And this is basically a system where we use software components and hardware components in order to speed up energy profiling and in order to help developers optimizing their program code. We also have a couple of people working on soft and hard energy systems. This is in correspondence to what you know from the real-time systems community with soft and hard real-time systems. And we also adopt methods from their research, and we extend it with genetic algorithms and iPad analysis. We will have a poster on that at OCI later next week. So if you are there, please come by, have a look, and talk to us on that work as well. So next up is my talk on proactive energy-aware programming. This is joint work with the Technical University in Braunschweig, and I will quickly go over and make a summary of what we are currently facing with regards to what are the current problems on energy-aware programming, or in general in optimizing program code for energy consumption. So people are currently writing, modifying, and building application code, and in the second step they are actually analyzing what has happened, whether a change of the source code has been a good one with regards to the energy footprint or not. And for that, they actually run the applications with defined input. So in order to verify that a change of the source code with the same input has a probably different footprint with a different algorithm or another change of the logic. And you can either do that with running your application with fixed parameters, or just simply reusing a use case which might be already available for your program you're trying to optimize. And in the third step, which is also a very resource-intensive task because it's just consuming time, it's a manual task again, you have to perform an energy analysis of what you are currently doing. And for that, you either use some hardware or software measures. So either you're using a measurement device in order to measure how much energy your application is consuming on a target system, or you're using some software profiling mechanism like energy profilers, which do not actually do any energy measurements, but they're doing some sort of an indirect measurement by using, for example, performance counters to see how many wake-ups an application has been causing. And then this is probably related to the energy consumption footprint. Or they use simple energy models, which are probably instruction-based energy models. So the current challenges to make that three-step approach a more efficient one is actually combining those steps in a way so that they get a more automatic thing, that they are not driven manually by the developers. So we are looking at integrating tooling infrastructure for energy-aware programming into existing IDEs. So we don't want to have people adopt to a completely new environment when they are doing their software development. And we are also looking at fully automated accurate energy measurements, because this is currently where the developers actually spend the most time, because it's just a very time-consuming task to run energy measurements for each and single application at a given workload. And last but not least, we also look at the challenge that actually developers often have no clue what they actually should do in order to improve the energy impact of program code. So this is really something where tooling infrastructure would be a great benefit for a developer to receive suggestions generated by some system in order to get an idea what could I change to potentially optimize my code. And we actually address those three challenges with our proactive energy-aware programming kit called Peak. It's a systems approach to energy-aware programming. We do integrate all that at the development time. So we do energy analysis right at the time of development. And we show in our evaluation that we can increase the task of energy analysis by a factor of 8.4. And at the same time, we were able to show that by creating automatically generated optimization hints, we could decrease the energy demand by 25%. So I will first talk about the design and the system architecture of our system framework. I will first talk about the software aspect of it, and then I will go over to the hardware aspects, which especially focuses on the energy measurement platform we have been developing for Peak. So the system is grouped into a front end, a middle end, and a back end component. And the front end is basically what we currently have as an IDE or an editor. It's basically the system where the programmer is writing his or her code. And that's basically where we get our source codes from, and where we also get the information on how to build the source code and how probably we are advised to do the energy analysis at back-end level. The second component is the middle end, which is a passive component, which is simply reused from existing development environments. So that's not a component we provide with Peak, but we reuse it. And that's where we actually simply store our data. This includes the source code, build data information, and metadata, which eventually controls the back end with regards to what it should do for energy analysis. And at the back end level, we are actually doing the most complicated stuff. So at that point, we are running the energy measurements. This is either a direct or an indirect one. So when I talk about direct measurements, it's usually using an energy measurement device, and if I talk about indirect methods, it's using a energy profiling tool. And what they all have in common is that they provide energy consumption values at function level. This is what we have chosen to do. We could go on to other abstraction levels, but currently we use that and turned out to work pretty good. The second thing the back-end infrastructure is actually implementing, that's the second contribution of our work from a software point of view. It's where we are actually generating energy optimization hints. So those are the suggestions we are passing through back to the developer when we have found things in the source code which could have been improved in order to reduce the energy consumption. And we pass those energy optimization hints back to the developer at the end of source code patches or modification to the build environment. It's very important to not only look at the source code, but also have a look at the build system. We will see in the evaluation that especially choosing the right compiler for a specific software is very important in order to reduce the energy demand. So when we look at the operations, how this all works from a developer point of view, we first have the developer to commit a snapshot of his current work. So this is the software combined with the energy analysis configuration. And we use for that simply Git. So we can reuse the whole Git infrastructure used by projects for our purpose of energy-aware programming. And for that, we are mapping a Peak snapshot to a Git branch. So we are working a lot on Git branches in order to evaluate how the different Git branches are with regards to energy consumption. And we can also use that for multiple snapshots. So for example, if you have probably 5 or 4 different implementations of an algorithm, you might want to just simply try out which one is the most energy efficient one for my source code on a given hardware platform. And for that, you simply submit a batch analysis through a couple of Git branches to our system. So once we have submitted the data to the middle end, we simply inform the back end that we are ready to start the energy analysis. And this usually is an asynchronous operation, because it might be that the energy analysis takes hours or days even, depending on the size of the amount of Git branches and the runtime complexity also of the code. So this is just something also where we have decided to really split the two systems into the front end and the back end, so that we have a separated machine running all the energy measurements, and that we don't have to do that on a developer machine. This is also very important for the aspect that we actually do real energy measurements. This way, we just have a dedicated machine with the energy measurement hardware, and several developers can share that one device rather than buying 20 of them. So once we have advised the backend to start the energy analysis, the backend actually pulls the Git branches to a local copy on the system of the backend and prepares the energy analysis. And at that, we then differentiate between the indirect and the direct measurement. We either deploy the binary to a target hardware platform and then run the energy measurement with the energy measurement device. Or on the other hand, if we use indirect energy analysis, we simply set up an execution environment with the energy profiler and then run the application under the supervision of that energy profiler in order to run the energy analysis. For the second step on energy optimization hints, let's have a quick look at how we actually can optimize software for energy demand or for low energy demand. So first of all, today it's the most important thing to actually exploit the available hardware energy saving features at a maximum. So it's usually that we have to find an optimal set, which depends on the structure and the runtime behavior of the source code in order to exploit it in the most efficient manner. And we then have to apply software changes to use those energy saving features in a correct set, or we have to restructure the software in order to make it more energy efficient, for example, by choosing different timers. Yes, please?
How do you strike the balance between performance and energy? That seems like a fundamental balance that developers have to strike.
Okay, so usually if you also have implications like functional aspects, like you have to meet a given deadline, which probably is caused by some performance constraint. You probably want to check that with a specific use case. So in case we are optimizing something for low energy, which probably now runs at lower performance, takes longer probably, you would have to, as a developer, check that our optimization does not interfere with probably performance or timing constraints you have from your point of view.
Okay, so the trade-off between performance and energy is not built into the system. The developer still has to write it.
Yes, but I think we will see in our, I will show some evaluation results which pretty much sums that up, because the energy analysis results, they not only give back how much energy your application has used, but also how long it was running, which again depends on the performance you are requesting. And we can, we still have the developer to make the call whether they need an application to finish in a specific time, like an interactive application, or whether it's some sort of a batch operation which can finish at any time, but run at lower energy footprint, probably for a longer time. What also is important is to align timers, for example, that you don't wake up the CPU too many times. This is probably also something you have to look at. And for our system, we currently have implemented.
Before you go to the next bullet,
Yep.
can you give some intuition for how an automated system can make suggestions about aligning timers? I mean, I can imagine, I've written code
Yep.
where we've got one thread over here that says this is how often I'd like to run another thread,
Yeah,
so
yeah,
it makes up
yeah.
the number for itself.
Yeah.
And it's not at all obvious to me how an automated system could look at that and say, these could be aligned even if, without sort of
Yeah.
knowing what constraints
Yeah.
were imposed on the selection
So,
of
yeah.
the time phase.
So actually, yeah, we have not yet done the automatic aligning of timers with our energy optimization hints. So that's just what we can do today manually. But you already have probably infrastructure in your operating system kernel where you actually see when threads are waking up the CPU, and you probably just can try to align them and double check with a use case afterwards.
Are you saying that the thing that Pete can do is give me a measure of how badly my timer selections are
Yeah,
interacting?
I mean, eventually boils down to that, because if you give me two different versions of your code where you have changed the timers, we will tell you what version has been better with regards to the energy impact. What we are yet exploring is how we could tell you what would be the correct order of timers and when should they fire.
Yeah, well, I can see how you could tell me whether what the overall consumption is. I guess what profilers generally do, performance profilers, is give you some hints about what problems are big problems for you.
Mm-hmm.
And so I can imagine that it might be useful. Maybe this isn't something Pete does yet.
Mm-hmm.
But I can imagine it'd be useful if Pete could tell me either, timer selection might be a big problem for you, or no, go look somewhere else for
Right.
making these
Yeah.
functions.
Yes, I think this is something we have not yet covered, but at the backend analysis, we definitely can look at things like that, because during the measurement we have to execute the code, and we can do such monitoring whether you had a lot of interrupts coming through or not. So yes, and yeah, I think the thing about what we currently explore with the energy optimization hints is more on the side that we simply use different power states of our hardware, and we explore whether using one energy saving feature is more energy efficient or the different one. We haven't yet looked into so much how the dynamic aspect would probably also benefit for lowering energy consumption. Also, what you say, it's probably interesting to. Currently, we're only optimizing more or less statically, but it's probably also interesting to actually implement something into the scheduler where you probably investigate what kind of input parameters are currently used by your application, and we've probably profiled that earlier with Peak, and we then probably switch to different energy-saving features or use different timers. So this is probably where we might heading with that. Yeah. So at the optimization level of the backends, we take the original source code and we analyze whether we find any functions where we currently have an idea they might be running at a lower energy demand if we switch the power the power saving features, energy saving features at that point, and we simply apply those changes just on trying it out whether it actually affects it, and we push back those changed snapshots to the Git repositories as a private branch, and this is where we then start another energy analysis for those modified branches. They might be completely bogus and they might crash, they might just be unusable, but they might also be just running fine. They might just fulfill the functional requirements of the original source code, and they might have a lower energy demand at the same time. So this is what we are then analyzing. From the candidates, from the private Git branches, we are analyzing during the next step. We then select the ones which actually show a lower energy demand. All others are just being deleted afterwards. And we do not yet generate the energy optimization hints. Sorry, we are not yet generating them. We just store the source code back to the repository and let the front end then generate the energy optimization hints. So this is actually being performed in the fourth step. So we simply have the back end commit both the energy analysis results as well as the potential optimization candidates to the storage middle end. And we then proceed in the front end to actually get those results, and the energy results are simply presented to the developer either with the used IDE or just by displaying a set of functions, how much energy they have been consuming. And for the optimization hints, we actually generate a diff between the original source code and the optimization candidate, and generate patches for the developer, but still it's up to the developer to really make sure that this source code or this application still is usable, still fulfilling the functional requirements. So it's not at a point where we can really go ahead and say, okay, we have optimized your program code and it's ready to go, but it's rather than we present a suggestion, this might be better. It's at least better with regards to energy consumption, and it might still be what you are looking after for your implementation, and then it's up to the developer to actually verify that. To get out the last manual step out of that would be really to use existing use cases for some software project, where in case the use case is strict enough to actually check all the functionality you want to have for your application, it's certainly sufficient to check whether all those criteria are still met with an optimization candidate provided by our system. So this basically completes the software side of our stack. The second part of Peak is really the energy measurement device, which we have implemented. And it's a follow-up work from our C paper. So we have really struggled finding a good way to measure energy consumption of different systems. So either you use an oscilloscope multimeter or an analog to digital converter, and usually you have the device under test and you have a shunt resistor afterwards, and you simply measure the voltage drop across that shunt. However, all the listed approaches on that slide, they have a common problem. They have all sampling constraints. So if we look at the limitations, they also have other limitations, like probably missing control interfaces, which makes it unusable for a systems approach to be used by another computer. But it's really that sampling may invalidate your energy measurements. And we show that by the following slide. So what we, sorry?
Are you going to define what that means? What that sentence means? Sampling can invalidate measurement results?
Yes, that's what I'm going to talk about. So for that, that's basically just an example why those approaches are difficult or even error-prone for measuring energy.
Right, I just didn't understand what that meant. So
Yeah, okay. So if we look at the following slide, we have measured the energy, or in this case, we had a constant voltage, so we measured the current of the device under test. That was I think it was an ARM Cortex-M4 microcontroller. And we did the energy measurement with three ADCs chained. And those three chained ADCs, they reach a sampling rate of 7.2 million megas, 7.2 million samples a second. And that translates into a sampling time of 140 nanoseconds. Yes, please?
By chaining them, are you assuming that the samples are interleaving, or being interleaved between the three ADCs?
As far as I know, it's
Your
right, yeah. And they are built onto the STM32F4 microcontroller. So you're simply using those three ADCs on that microcontroller. Yeah. And we can see the sampling time in between the blue lines. So everything in between goes potentially unnoticed by your measurement device. And if you're really looking after the area below the current, that's basically the energy. We multiply the current with the voltage times the time. And we can see that there's a lot happening in between. And if the measurement devices are not prepared to somehow capture that current, you probably lose quite a bit of energy in your energy measurements.
So you don't really mean that sampling perturbs the system. You mean the sampling system doesn't have the fidelity required to measure it.
Yeah, that's what the bullet before.
Okay, so this was confusing.
It's not invalidating measurement results. It's
Right. Oh,
less precise.
yeah.
I mean,
Yes.
Because you're going to integrate between the two.
That was just a bad translation. I know what you get. Yeah, that's good to know. Okay, I will change that. Yeah, thanks. Yeah. It doesn't change. No, it doesn't change the energy. Actually, it does also change the energy consumption of the device. But yeah, it's not much. It's just, yeah, that's perfectly fine. That's not much.
Right. But,
Yeah.
okay.
So,
You're
yeah.
still going to integrate, though. I mean, the question is, this basically bounds your error
Yeah.
measurement, right?
Yeah.
You're going to integrate between these two, and you're going to have some
Yeah.
number of joules that you consume, and
Yeah.
you've got true joules. And the question is the difference, does the difference matter
Yeah.
compared to the execution of the program?
Yeah,
and the
yeah.
time.
Yeah.
I mean, if your base part of the device is 3 orders of magnitude higher than the other, then you consume that. It's
So,
unclear whether or not what you're missing matters.
Yeah. So we are currently on a second hardware paper where we are actually exactly looking at that. How much is the difference between using a multimeter, a changed ADC approach, or an oscilloscope compared to what we are doing with our device?
To generate that.
This one was measured with a high-end oscilloscope.
That was doing like gigahertz or something.
Yeah, something like that. Or even more. I don't know. Yeah. So this has been done in the lab.
The problem with the oscilloscope is that it's got a very small buffer, right? So
Yeah, you cannot do it. Yeah, you can do it for like a snapshot, short time, but not for like 5 minutes. And we can go with our device like forever. So yeah. And actually, often enough, you're not actually interested in something like that. You don't need the temporal resolution, but you're interested in having the entire energy consumed through a run. You're probably just interested at function level, not at like instruction level. You probably don't care. I think, I don't have the data with me, but I think the Cortex M4 we have been measuring here is running at 160 megahertz. So yeah. And it's pretty much impossible to make that deterministic. If I run it a second time, you will certainly see the instructions, but you will see everything else too. So yeah. So what we have come up with is an analog energy measurement device. So essentially, that's the core of it. We have the device on the test over here, and we have the current trained by that device over those 3 transistors, and that's implementing a current mirror. And that's where we probably get back to the topic of not changing the energy measurement or having no impact on the measured energy. So what is happening here? The transistors in the current mirror, they create 2 separate additional currents, IM1 and IM2, which are of the same size or same. They are equal to the original current ID. So we have 3 currents which are of the same size, but after that we are only analyzing IM1 and IM2, and we don't interfere with the original current drawn by the device under test. And we have, as a second thing, we have here a flip-flop, which is controlling those 2 capacitors to be charged and discharged on an alternating basis. And this eventually leads to such a square wave signal, which together we simply count how many charging and discharging events we have been seeing through the measurement. And under the knowledge of the size of the capacitors, we are then able to extract exact energy values. And that's just what you are looking after. So this is also the feedback we got from our prototype. But the prototype really was something like that. And this is something you cannot give out to anyone, even not to other researchers. So today it looks like that. We have a fully integrated energy measurement device, which integrates the current mirror at the hardware level and provides all what you want, like a USB port to actually access the device to control the measurements. And yeah, I've got some technical data there. We have an energy resolution of 0.1 microjoule, which is fine for our even the smallest devices we are dealing with, like the smallest Cortex M0 Plus ARM microcontrollers. And we have a temporal resolution of 6 nanoseconds. So if this is still not enough, you really have to get back to executing stuff in a loop and then dividing the results. But for what we are currently doing, it turned out to be sufficient. One
10 seconds is about your instruction clock rate on this device, right?
Yeah. Yeah, but if you are measuring something which is probably shorter than 6 nanoseconds, if you measure something else, like a device which changes over the time more quickly. So yeah. One thing we are also we had to integrate is this thing here. It's a cooling part of it. So this actually the weak spot I will talk about just for a second. The transistors here, they are pretty much maxed out by doing all that work of carrying out the mirrored currents to the current mirror. And that's currently in the works that we go further. That eventually, or today at least, limits our device only to be suitable for like embedded devices. We can, I think, cope with a current of about 500 milliamperes, but everything above is a problem. We have a solution for it, but it's not yet ready. So the easiest solution is to have another second device ahead of our current mirror, which simply scales down the current to a smaller one. But then this has also to be hopefully very correct and precise rather than generated by some sampling. So this is, that's the device we are currently working with. We will actually release the schematics as open source. So we will not keep it in our lab. We will give it out to anyone who wants to work with it. We already have a couple of groups in Europe working with it, and I think we would look forward to what happens after trials, because then it's probably known to enough people who probably have suffered from exactly what we've been through for doing energy measurements earlier. So last, I will give some evaluation results of PEAK, of the joint software and hardware framework infrastructure. So I will not talk too much about the time savings and hands-on experiment which we have carried out. I will focus on two things or three things. So we had a couple of benchmarks which we compared with regard to how runtime relates to energy consumption. And today's best practice is a strategy of race to sleep. So you usually execute something as quickly as possible at the penalty of a high performance, high power drain, but then we can sleep for a long time. And in our evaluation, we show that this actually sometimes is inverted. So sometimes it's really true that it's better to keep something running for a long time, and the total energy footprint nevertheless is smaller than executing it very quickly and then sleep for a long time. Second thing of this energy measurements is comparing the energy efficiency of program code generated by GCC and Clang. This will show that choosing your correct compiler is an important thing to consider. And third, we will show how we were able to speed up the code using energy optimization hints in our evaluation demo application. So this is our evaluation platform. Again, that's a very small one. It's a Cortex M0 Plus MCU, which clearly shows we have already to deal with 11 different power-saving features on that small microcontroller, and it doesn't seem to get better. So it's really something which will not go away anytime soon, at least as long as we have energy as a resource we have to consider on our systems. And for the first evaluation results where we look at the power modes, we have been executing different benchmark modules. We have like 12 in the paper, and I've picked out 3 interesting ones for our presentation today. And you can see the runtime of those benchmarks running in different power modes and the corresponding energy footprint. And for like 10 of, or 9 at least, of the benchmark modules, we pretty much see something like for the CNT example on the left. When running in a low power mode, it takes a long time to execute. It is much quicker when executing it in a normal power mode with a higher clock speed. And at the same time, it's usually that race to sleep, executing it quickly, sleeping for a long time, is actually more energy efficient. But for 2 examples, for an insertion sort and recursion algorithm, we saw that this actually is inverted. So for those, we still have the speed up. It executes much quicker when running in normal power state, normal power mode. But if you look at the energy footprint, you can see that during that short time, you actually consume higher power times time goes to the higher energy footprint for the 2 benchmark modules on the right. So this is something interesting, and this is something we really have to look into, because if you experience something like that in a task which does not have any tight schedule or deadline it has to meet, it's just nice to execute it whenever you want at a low performance, but eventually you will save energy. So this is one interesting aspect of our evaluation. The second one was who's going to take the win for the best binary created by a compiler. And for like most, I think 9 out of 12 benchmark modules, we had similar situations like the first two. One time it's the GCC compiler which is generating the more energy efficient code, and the other time it's Clang. So it's like 5 times it's Clang, 5 times it's GCC, which already, I mean, it's already showing a difference of 20%, which shows you really should pick the right compiler for your application. So
that we have no idea how
yeah,
compilers predict
yeah,
this.
exactly. So
Right.
yeah,
It's not that you
yeah,
just
yeah, yeah, exactly.
But at least in all of these,
Yeah.
fast code is correlated with energy efficiency.
No, not on the
Huh.
last slide. The last one.
Huh.
On the other slide, faster code was
Yeah,
shows more energy.
so
Oh, but
actually-
that's when you're teaching the process of power mode, right?
all right, yeah, 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 yeah. That's true. Yeah, yeah.
Through the fast code.
But still, if you can save like 1/5 of your energy by speeding up your code by 20% without paying anything but switching the compiler.
Oh, no,
Yeah.
I understand that.
Yeah. One interesting benchmark was the cover benchmark, which actually showed that GCC was just slashed by Clang. So we see that Clang was executing the code in like a fifth of the time GCC was executing it. And we looked into the binary of that, and we saw that this is due to some interprocedural optimizations, which were only available in Clang. So this is really where you see that energy really depends on the optimizations of the compiler. Yeah.
Did you run into any examples where the energy consumption was nonlinear with the performance improvement? So, or put another way, was the improvement in energy consumption always proportional to the improvement in runtime, or were there cases where the runtime only improved a small amount, the
Nah.
energy improved a large amount, or the runtime improved a large amount, the energy did not?
Like in the first two examples, usually it's correlated that, very closely. I think, yeah, pretty much the 8 examples I left out look like the first two, just sometimes it's Clang, sometimes GCC. Okay, third thing was our evaluation of the optimization of program code by automatic generation of energy optimization hints. So what we used for that during our experiment is we had a contiguous application which consists of 2 functions, 2 tasks. One is sampling data from accelerometer, and the second task is using this data. It runs an AES encryption and sends it out using Wi-Fi. Sorry, not Wi-Fi, wireless. I think it's just some Zigbee module connected to the device. And in the evaluation results, we simply for the evaluation we just took our system to automatically switch the tasks to different power modes, and then check how is the energy footprint for the application. And we could see that for the original revision, which we received from the developers, where both tasks have been executed in a low power mode, could be cut down to from 10.6 millijoule to 7.6 millijoule. Yep.
So in this case, task 2, which I guess is the transfer task,
Yep.
is one of these funny tasks like insertion sort recursion, where going slower makes it safer.
Yeah. Yeah. Right.
So
Yeah.
that's the special class that task 2 is in.
Oh, actually, it could be, but I don't know whether this is really was true for that.
I mean,
It doesn't have to actually.
you think if that's not the case, then there must be some.
Oh, you're right. Yeah, you're right. Yeah.
But if they're independent, then
Yeah, but yes, I think they were not completely independent. That we had situations where task 2 had to wait for task 1 to finish sampling, for example.
But once it had waited, you switched
Yeah.
to a low power mode to run task 2, right?
Yeah.
That's
Yeah. Right. I see what you mean. Yeah.
I mean, the lesson I'm trying to extract from this, and I'm curious if you agree with it, is that task 2 is actually an instance of one of these funny tasks where performance is not the same as time.
Yeah. I mean, I don't have the exact numbers how this is split up between the 2 tasks right now, but I definitely will have a look at that. It really, I think it should be like you say. It must be, probably. I double check. So we also see that it's not always the case that we succeed. So this revision, for example, would not have been in the selection proposed to the developer. So yeah, that basically shows that revision 3, which we generated, saves 1/4 of the energy of the original source code, which is pretty good for an automatic optimization, I would say.
That's the energy of the entire device, right? Not just the energy of the microprocessor.
Yeah, it's everything. Actually, it's difficult to on those devices. I mean, you saw that thing. This is everything. I mean, it's impossible to measure the memory and the CPU
Right.
separately. So
Right.
it's
You're getting the device you measured, the integrated device you measured is the total DC current draw.
yeah.
But you're not measuring, for example, the cost of operating and the power mode for the wireless transmitter.
No, that was externally. Actually, for this hardware platform setup, for this one, we measured the entire device. So we had something like this one, which has this ARM Cortex M0 integrated together with the ZigBee modules and everything connected. And at that level, of course, we could look into what's the difference between the ZigBee consumption and the CPU consumption. It's also something we are currently looking at for future versions of Peak, because, I mean, you're really interested in not only the total power consumption or energy footprint, but you want to see, okay, where can I save something? Should I reduce the memory accesses? Should I reduce the Wi-Fi or wireless transmissions? So that brings me to my concluding slide. So I've presented Peak, a joint hardware and software framework for energy-aware programming. It seamlessly integrates into existing development environments. It doesn't change too much. It's only adding a few components. And it assists developers at the task of energy-aware programming. As future work, I've put some points on the slide. We really want to, we will release the core components at least on an open source license. We might even look into producing the PCBs and the measurement devices and sell them. They are like, I don't know, I think we have a number in the paper. It's like $80 or something. It's just nothing compared to any of the other energy measurement devices, which are not as easy to be used as ours. So we might look into producing them and selling them, but yeah, that's just, it's future work. Other than that, we further will improve the energy measurement device. As mentioned, we still have to deal with higher currents, so we're looking into this as well. And we also want to see how we can also integrate further energy profiling mechanisms, which are using software components only. So yeah, that's pretty much it. So if you have any questions, please go ahead. Yeah, that's good. All right. Okay. Thank you very much.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.